in terms of our class today, we're going to be talking a little bit about orbital motion, along with a couple other things. So, anybody want to tell me why it is the house went to the doctor? Why did the house go to the doctor? I like that answer. I think I like that better than the answer I have. It was having window pains. What?
Oh.
Okay. So let's take a look briefly at worksheet number 2, and then we're going to go ahead and get into what we're going to get into today. So worksheet number 2, page 1, just a couple things I want to point out about this. For number 1, letter C, when you're calculating how heavy guile feels at the top of the loop, you're going to do this the same way you did all the other problems with the force diagrams of things that were moving in a circle. You know, if you're at the top of the loop, you've got two forces. You've got gravity down, and you've got the normal force from your seat down, as long as you're going fast enough. So your force equation is simply going to be normal force plus force of gravity equals MAC, because you're moving in a circle. So if you want to figure out how heavy he feels, you're going to isolate and solve for the normal force. You've got all the other pieces of information to do that, so it's a pretty straightforward thing. If you're doing the same thing for the bottom, then you would just change this plus to a minus, because at the bottom you have normal force up and gravity down. So you'd subtract the two, and you'd get a different number. Of course, at the bottom you're going to feel heavier, and that should come out in this example. For the bottom you should get 1150. For the top you should get 72.5. One of these that I would like to go through all the way, though, is number 2. And then we'll do page 2, and that should be good. So number 2 says, now he's back at the top of the loop. We're wondering how fast he needs to go in order to feel twice his regular weight when he's upside down at the top. So if we want to figure that out, we're going to use this exact same equation, because he's in the exact same position. He's on the very top there. So normal force and gravity are still headed in the same direction. The only difference is we're looking for the exact speed at which he feels twice his regular weight. So if you regularly feel like you weigh whatever your force of gravity is, then twice your normal weight would simply be equal to twice your force of gravity. So you would simply take your normal force, change it to 2 times force of gravity, add it to that, and you'd see how it plays out. So let's just see what happens here. 2. Yes, that's how easy it is. 2mg plus mg equals mass. And centripetal acceleration, remember, that's v squared over r. So if you want to figure out the velocity, the first thing you can do is get rid of the masses and then multiply both sides by the radius there. So 2g plus g is equal to 3g. So 3g multiplied by r equals v squared. Take the square root of both sides, and that will get you that velocity. And that velocity is going to come out to be 106 meters per second. And that would be your answer there. Questions on this? Alrighty, let's take a look at page number 2 then. So this is the really, really hard one.
Yep.
There were 2 people that figured it out.
Oh.
Marta and Brooke.
What?
Yes. So let's take a look at problem number 3, which is on page number 2. So this is the example where you jump into that carnival ride that spins around fast, 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 and you get pushed to the wall like that. And the thing is, after a while, the floor drops out, and the friction between your back and the wall is going to be great enough that you actually don't slide down. You don't need the platform underneath your feet, because the friction between your back and the wall is great enough to stop you from sliding down. So in this example, let's just kind of set this up because it's asking for the maximum period necessary for it to go around once and you to be pushed hard enough against the wall that you don't slide down. And that's going to be a bit of a process. So the best thing we can do is just start with some forces, and hopefully that takes us somewhere. So our forces that we're going to be looking at here are vertical forces. You've got friction actually going up in this case, and you've got gravity trying to pull you down. So that's the first real tricky thing to try and think about. We're not used to friction going in the opposite direction of gravity. And of course, if we're looking for kind of the minimum speed necessary, which would be the maximum period necessary, then we're going to be ultimately setting these two things equal to each other. This would tell us that our force of gravity is equal to the force of friction. In other words, you're just barely not sliding down. So, any questions on why this equals this? Okay, so force of friction, remember, is equal to coefficient of friction times normal force. So all I would do to rewrite this is I'm going to take that force of static friction and I'm going to rewrite it as coefficient of friction times normal force, and force of gravity, of course, is going to be equal to mg. And here's the other tricky part then. When we're dealing with centripetal force, the forces that are acting, causing something to move in a circular motion, when you're spinning around in this circle, which force is making you move in that circle? Anybody tell me? Which force, as you're spinning around and around, if you got rid of it, would cause you to stop moving in a circle? What's it? Almost. Centripetal force would be the correct answer, and that takes a certain form in this problem. Normal force, yeah. So your normal force is the only thing keeping you moving in a circle, which means your normal force is actually equal to centripetal force here. So in that case, centripetal force again is mass times centripetal acceleration equals mg, and centripetal acceleration is v squared over r. And now we can solve for a velocity, which would get us halfway there. So if I want to solve for that velocity, I would multiply both sides by r and divide both sides by the coefficient of static friction. So let's see. So v squared equals grr divided by coefficient of static friction. And of course, if we want... Oh, that's going to look fun in the video. So if we want to get rid of the square, we have to square root both sides. So there goes the square. Here comes the square root. And you can plug those numbers in. Once you plug those numbers in, you're going to get a velocity equal to 5.42. And that is your velocity there. And once you have your velocity, now you've actually got enough information to figure out the maximum time necessary to go around once. Because x equals vt. If we're looking for time, time is simply going to be equal to our distance over our velocity. And our distance in this case, when you go around once, that is the circumference. So that's going to be 2 pi r. And the velocity is what we just found down here, 5.42. And when you go ahead and do that math, you'll end up with a maximum period of 1.74 seconds. What's that? All right. Any last questions on this one? I suppose we should just forget all about this, huh? I don't blame you. That's a tough one.